So on PSpice, till now I've simulated more than 20 number of projects. But before starting a discussion on the complex ones, I wanted to tell you a very familiar chip, and we all know about it, that is OPAMP. And we have done so many experiments with OPAMP during our college days. So today in this tutorial, we're going to discuss about how to simulate non-inverting and inverting amplifier. After that, we'll just record its, or we'll simulate its frequency response. Then we'll plot this Bode-Plot, and we'll try to see after 50% power what is the amount of voltage we are getting and at what frequency it is kind of stop working, or there will be a lot of attenuation on voltage after a certain frequency. We'll see that. Then we'll do the same thing, this first and second analysis on inverting amplifier. After that, I will tell you some small points about active low pass filter using OPAMP, and and then we'll do all these analysis like AC sweep, Bode-Plot, and transient analysis on low pass filter using OPAMP. So yeah, this is a kind of type of topic we're going to discuss in this video, and I hope you will enjoy the content. So with that said, let's roll the intro. So before starting the simulation, I wanted to tell you a little bit introduction or the background about this non-inverting amplifier. I guess you people have used it long time back. So let's see how it looks like. So this is our amplifier symbol, right? Here we have this non-inverting terminal. Here we have inverting terminal. This is our V out. So this is our V out, and here we'll get VCC and VEE pins, where we can connect positive and negative voltages. And so in this, in case of non-inverting amplifier, we'll connect our source or input signal in non-inverting terminal. Let's suppose this is Vs, right? And on inverting terminal, we connect two resistors. One is input resistor and one is feedback resistor. All right. So one is connected. Let's suppose this is R1, and we connect one more resistor. Let's suppose this is R2, or we also use this term RF for feedback resistor, right? That's it. This is our non-inverting amplifier circuit, right? And for this, what is the gain of this non-inverting amplifier? This is generally 1 plus RF upon R1, right? That's it. So I just wanted to tell you quickly how we get this 1 plus RF upon R1, because this is the main thing. That's why we use amplifiers. That means we have to amplify something, right? So let's suppose RF is 10K, or okay, let's suppose RF is 9K, R1 is 1K, and we are giving 1 volt. So what is the gain? What is the V out we'll get? We'll get 10 volt here, correct? So we'll apply KCL on that. For applying KCL, let's suppose from here the current is flowing I in. Let's suppose this one will be I1, this one will be I2, right? And here I in will be equal to I1 plus I2, right? Now the people who don't know, here we have a very high impedance here on this one. So that means I1 will be almost equal to 0, right? So in this, I in will be equal to I2, and if we'll see what is I1, what is I in will be 0 minus VA, right? So 0 minus VA divided by R1, and I2 will be VA minus V out, right? So it will be VA minus V out divided by RF, right? And if we'll do these calculations, we'll get V out divided by VA is equal to 1 plus RF upon R1, right? And here VA will be is equal to V in, because of very low amount of current which is flowing. So that means there will be 0 voltage drop, right? So those voltage, so here VA will be is equal to V in, right? So this is small derivation I wanted to just tell you, so you can, you know, kind of recall things, what is non-inverting amplifier. Now we'll move to simulation part. All right, so let's move to simulation part. So for that, we're going to use PSpice from Cadence. Let's open that. All right. Okay, now we're going to create a new project for this amplifier simulation. So we'll click over File, New Project. Now here you have to select location where you wanted to save this project. So I'm just going to use my desktop folder, and here I'll create a new folder which will be our level 2. All right, select folder. Now you have to name the project, so I'll use level 2 OPAMP. Here I wanted to discuss one more thing. So here, as you can see, we have one option which is enable PSpice simulation. As I told you, for 17.2 it will be mixed signal, analog and digital simulation enable, but in case of 17.4 it is PSpice simulation. So you have to check this mark, only then we can able to run PSpice simulation on our project. Now press OK. Now it is asking for you wanted to create some project based on existing project, or you want to create some blank. I'll select this another option, press OK. Alright, so our project is created. Now here, as I told you in level 1, in 17.4 we'll get an option PSpice part search, right? That is not available in 17.2. So for that, what you have to do, you have to add libraries manually using this place part option, and here you will get this option add library. If you click on that, you will be directed to the default folder where we will have all the PSpice libraries, right? Now, which 3 libraries you need to add to run this simulation? As I told you on level 1, it is analog, eval and source. In case of 17.4, you don't need to add any library because it's already, we can able to search any part through this PSpice part search. Now we're going to place operational amplifier first. So for that, we'll search a part number which is UA741. All right, you'll get couple of options, right? But I found this part which has all the pins clearly mentioned, so I'm going to use this one. If you double click on this, you can able to place it. Now right click and left click over end mode. All right, so this part is ready. Now I'm just going to flip it quickly because I want this non-inverting terminal here and inverting terminal here, right? So I'll mirror it vertically, right? So you can see it is kind of flipped. Now next step is we'll add our DC sources. So for adding DC sources, we'll just search here VDC and enter. Now we'll have our DC sources. Why I'm placing 2 DC source? Because it will be positive and negative bias both. All right. So next step is we're going to add grounds on these 2 sources. Let me shrink this a bit. All right. All right, now it's fine. Now we're going to add ground here. So I've already told you which ground we're going to use. End mode, we'll just drag it. Okay. Now here I'm going to tell you few more things about this PSpice simulation. So like we use ports and nets during our normal schematic design, the same kind of schematic we can design for PSpice simulation. So we can place port, we can place nets on different sources or different components, right? So I'm just going to demonstrate how to place ports here. So for port, you have to select left capsys port, okay, which will be this one, right? Press OK and we'll place it on both of these end mode. Just drag them little bit. All right. So let's add value for these DC sources. So for that, double click over this text, and this will be our 15 volt DC, and this will be minus 15 volt DC. All right. Now we're going to name it. So this will be VCC and this will be VEE, right? This is what we use, or VSS, we can use VSS as well. All right, now we're going to copy and paste the same port for this V plus and V minus. All right, so V plus will be connected to VCC, and V minus will be connected to VEE. All right, let's drag it a little bit. All right, so this is already connected. Now we'll move to another part of the circuit. So for non-inverting amplifier, what I've already told you, we have to place input register and feedback register on inverting terminal, right? And source will be connected to non-inverting terminal. So for that we have to place register. So let's search for register and we'll go for general purpose one, double click. So one will be here, another one will be here. All right, these value will decide later. Now what is another component? Another component is we have to connect a source. So that source will be analog input. So for that we're going to search V sine wave, right? All right. Now before connecting all these open connections, I want to fill these values for V sine. So that values will be, so this is offset will be 0 volt. What will be the amplitude? I'll go with 1 volt. What will the frequency of the signal? We'll start from 100 Hertz. And so here, as I told you, we're going to discuss or we're going to run couple of simulations. We'll start from transient, then we'll do AC sweep analysis as well. So for that I'm going to put AC voltage as well. Let's make these connections quickly. So this will be connected here, this will be connected somewhere here, that will be our output, that will be connected to ground, and this will be connected here, this will be connected to ground. And okay, so here you can see these pins, which is OS1 and OS2. So people who don't know, OS1 and OS2 is pins that we use to basically cancel out, or you can say kind of tune whatever the offset we have, right? So in this case we're not going to use it. We don't want to cancel any kind of offset or eliminate any kind of offset in our signal, because there is no offset. So let's connect grounds quickly and then we'll go for simulation. So either we can copy ground or let's place one. So this will be connected to ground, this will be connected to ground. End mode. All right, so circuit is ready. All right, now another part is we have to run the simulation, but before that I want to recall couple of things that we have discussed during the first section of this tutorial. So we have basically derived this non-inverting amplifier, and from that we got what will be the gain of that. So what will be the gain of non-inverting amplifier? It will be A is equal to 1 plus RF, which will be R2 upon R1, right? So right now the gain is 2. I want to go for 10 gain. So for that I'm just going to correct this value to 9K. Okay. Now the gain of this amplifier will be 10. Alright. So let's add a small load at the output of this non-inverting amplifier. So for that we'll again, or we can just copy and paste, Control C, Control V, using R or rotate, we can rotate it. Alright. Let's place it, put another ground, we'll just copy it from here. Alright. So here I have one question. Now tell me what will be the amount of current which will be flowing through this load resistor, which is 1K. So as per our amplifier, the output voltage will be 10 volt, right? So that means the max amount of current which will be flowing through this resistor to ground will be 10 milliamps, right? And what will be the amount of current which will be flowing through this 9K feedback resistor, right? So that will be 0.11 milliamps, right? So you can do that calculation later. Alright, so now we're going to add simulation profile. So for that I've already told you, you have to just go over that button and left click on that. Now it is asking what will be the name of simulation. We'll go for transient first, right? So this will be sim. We can't use space here, so don't do that. And left click over create. Now it is asking for sorry, it is asking for some settings. So we're going to do transient. All right. Now here you have to fill few information, which will be what will be the run to time. All right. So run to time I'm going for, let's go for 100 millisecond. All right. Save data, no, I don't want to save anything. Let's fill the maximum step size. So this I'll go for 1 micro. All right. So here we have filled all the information required. Apply OK. Now next task is we have to add probes. So I'll add voltage probe on load. So one will be here and one I'll add at input. All right. So I've added these two voltage probes. Now before running the simulation, I want you to kind of assume or we can discuss, if you can, if you are watching it right now, just think that in your mind what will be the output of these, or what will read through these two probes, right? So here on this first probe there will be a sine wave of 1 volt. All right, and its frequency will be 100. Similarly, at output, frequency will be same, but the amplitude of this output signal or the second probe will be 10 volt, right? So this is what I'm expecting with respect to time, right? So on time, another scale will be time scale, and that y-axis will be voltage scale, right? So let's run the simulation and we'll see. All right, so simulation is running right now. It will take some time because we have put a high resolution. All right, so simulation is ready. As you can see, this is like 2 volt per division here, right? So this is 1 volt, this is 10 volt, and there is no phase shift, right? And we'll see a phase shift or a inverting waveform during the simulation of an inverting amplifier, right? So this is one kind of simulation that I wanted to show you, right? Now we'll go for AC sweep. So let's close this one quickly. And for AC sweep, we have to just edit the simulation properties or simulation settings. And here we have to select AC sweep. All right, that will be, so for AC sweep, okay, now before going to AC sweep, I wanted to understand, so this will be frequency response, right? And we'll get frequency on one axis and gain on another axis, right? So first it will be output voltage, then we'll use D function to convert it into, sorry, dB function to convert it into decibel gain, right? So what will be the formula of converting a normal gain, which will be V out by V in, to decibel? That will be 20 log of gain, right? So in our case, what it will be? It will be 20 decibel, right? Gain will be 20 decibel, all right? So this is something I wanted to tell you. Then we'll discuss this minus 20 dB per decade slope, and what will be the frequency after that. It will start attenuating. So why we do frequency response? We know that why we did transient response, because we wanted to see what is happening with signal with respect to time, right? So it is uniform signal, that we already know. But we also need to understand what is happening with our output signal if we have increased the frequency of input signal, all right? So we'll understand after certain frequency, the voltage will start attenuating. The output voltage will start attenuating. It will not be 10 volt anymore after a certain frequency. So that is why, to understand this kind of frequency, we do these kind of analysis. I hope you're getting my point. So on this, we have to fill few information, which will be start frequency, end frequency, and what will the points per decade. So start frequency will be 10, end will be 10 meg. So for meg, we'll use meg is nothing, it's a mega, and points will go for thousands. We always speak that. All right, and this will be logarithmic, and everything else will be fine. So here I hope you got my point. All right, now we'll apply and okay. Here we don't need to simulate this one, because the gain of this will be the voltage on this will be like a linear plot, right? So we'll just removing it. So we've already assumed what will be the plot. It will be constant for a particular for up to certain frequency, then it will start going down, right? So let's see that. Let's run the simulation. All right, so as expected, it started from 10 volt and then it started going down after 10 kilohertz, right? Now which value will pick, like which will be the cutoff frequency for this thing, right? So for that we use minus 3 dB, 50% power, right? And what will be that voltage? That voltage will be this maximum voltage divided by under root 2. I've told you that on a 1 minute learning of EsteemPCB. If you haven't watched that, please click over this I button. I'll put the link there, so you can directly go to that video. So if you'll do that, it will be approx 7 volt. All right, so I'll use marker and I'll put it to 7 volt, and we'll get frequency about 100K. Okay, so 100K will be the frequency. After this voltage will go below 3 decibel. All right, now to understand this, what we'll do, so it is 100K, right? What we'll do, we'll just double click on this. Firstly, you have to copy this trace expression, Control C. We'll select dB, Control V, okay. Now this is the decibel response. As we have expected, it started from 20 decibel, right? We have to go minus 3 dB. All right, so you can see that right now it is, we have to go to 17. All right, so on 17 it will be, so this is on 17, right? Not exactly, it's 17.0068, right? and on that we are getting frequency of 98.175k. So this is the input signals frequency which it can able to handle. After that, this amplifier will not get enough output. All right. So this is another kind of simulation I wanted to discuss. Now let's move to the simulation of inverting amplifier. Okay, so here for inverting amplifier, I have created another page which is already created, so it won't take much time to simulate. All right. So what is the difference between inverting and non-inverting amplifier? The source will be connected to inverting terminal and non-inverting terminal will be connected to ground. All right. That is the only difference. Now here I want the same gain. Okay. So the gain formula, if you again apply KCL and do all the derivation, you will find its gain will be A is equal to minus RF upon input Rin, right? So in this case it will be minus 9, right? But I want 10 gain, so for that it will be 10k. Let's make it 10k, and all other things will be same. Let's put some probes here. So you can see I have something else to show you which is on page 3 that I'll discuss after 2 minutes. Okay, let's put output probe and input end mode. Okay, now guess what will be the output. So this time also output will be 10 times of input, but it will be inverting. So if input will be going high, output will go in another direction, right? It will be on negative direction. All right. So let's simulate this as well. And here we go. So it will take little bit few seconds to simulate because we have simulated so many points here. But as expected, the output waveform should be inverted with 10 times of input. All right. So as you can see here, this is our red one is input signal and green is output signal, which is kind of inverted, right? So this is what we were expecting. Similarly, if you want, you can go for frequency response. Let's close this simulation, click over edit, go to AC sweep and logarithmic. We'll enter same values here, 10 and the other values was 10 meg, right? And number of points we wanted to simulate thousands, logarithmic, apply, okay. Here we don't want to change anything, just remove this and run the simulation. Okay, this is done pretty much faster. Alright, so at minus 13 dB. Okay, so here we'll observe one thing that is pretty much interesting, and you can put your answers in comment section. So in case of non-inverting amplifier, this frequency was little bit higher. Okay, this cutoff frequency was almost 100k, right? But in case of inverting amplifier, this cutoff frequency will be, or if we go for 7 volt, it is 91.83k. Okay, and the hint is this is happening because of feedback register in source. So this is the difference, right? So I just want you to put your answers in comment section why this cutoff frequency for non-inverting amplifier is higher than inverting amplifier. All right, so that's it. These are the few things I wanted to discuss. And here one more circuit I wanted to tell you. So using non-inverting amplifier by adding using inverting amplifier by adding a simple capacitor across the feedback register, we can make it an active low pass filter. All right. So you can simulate this as well. So the task is you can go for transient, AC sweep and DC sweep analysis. All right. So yeah, and I'll attach this project in the description. You can download it from there.